Hi everybody, welcome back. We're in chapter 5 and we're skipping section 5.2 because I'm going to assume that you have a working knowledge of what delta G actually is in relation to entropy and enthalpy and those things from General Biology 1 and General Chemistry. So we're going to take a look at really the meaning of delta G and a new variable in thermodynamics and enzymatics called the equilibrium constant K equals or K equilibrium. So let's get going with that. A little bit of math in here, so hopefully that's not too overwhelming. We'll go pretty slowly and I'll highlight some things as we're going along. So personally, my feeling about delta G and K equilibrium, the equilibrium constant, is that the equilibrium constant is often an easier thing to interpret the reaction kinetics from when you're trying to understand something about the system you're looking at. So I often actually prefer to look at the equilibrium constant over delta G, and we'll look to see the relationship between the two in a moment. So let's just consider a generic reaction where A is converted to B, and that reaction is reversible, and B converted back to A. So the equilibrium constant for this reaction, A converted to B and B is being converted back to A, is the ratio of the product concentrations of the product concentration and the substrate concentration. So the equilibrium constant here is the concentration of B, and those square brackets you see there, they'll always mean concentration. So the equilibrium constant is the concentration of the product B at equilibrium divided by the concentration of the substrate A at equilibrium. And so the reaction's at equilibrium, and so the rate of A being converted to B is effectively the same as the rate of B being converted to A. So that's the reaction at equilibrium. So that's usually calculated under standard conditions, and so that involves the starting conditions having the product and the substrate concentration both be at 1 molar. So you start the reaction like that, you set up the concentrations of B and A being 1 molar, and you add enzyme, and or you don't add enzyme, and then you look to see at what point does the reaction stop proceeding, and therefore A being converted to B is being equal by B being converted to A. And the ratio of the 2 points when the reaction of the product and the substrate when you get to equilibrium is B over A, so product over substrate. And you got to remember that, okay? Product over substrate is the equilibrium constant. That's what this number actually means, is that if you know the equilibrium constant for a reaction, and then you know whether a particular mixture of substrates and products, products and reactants, substrates and products, if you know that the mixture that you have in a reaction is not at equilibrium, you can tell in which direction the reaction must proceed to reach equilibrium. So here's a typical example here. The equilibrium constant, let's say, is 1, okay? And then this line here represents how the free energy changes as a function of the equilibrium constant moving away from 1. So if we had a reaction that had gone to equilibrium and we calculated what the equilibrium constant was, then as it moves away from 1, is what we see is that basically more free energy is either produced or needed to drive the reaction in the opposite direction. So if you have an equilibrium constant down here, less than the equilibrium constant, the reaction is going to be driven to the right. And if you have a concentration of B over A over here, greater than 1, the reaction is going to be driven to the left. So you've got your equilibrium constant, and that's being calculated in standard conditions, remember. So 1 molar product, 1 molar substrate, and you let the reaction go to equilibrium, and that gives you your equilibrium constant. If you find that the molar ratio of B to A is 10, so what that means is you've got 10 molecules of B and 1 molecule from A. If you don't believe me, do 10 over 1, it's 10. So if you end up with a molar ratio of 10 of B to A, then your reaction is going to be driven to the left. And if you end up with a molar reaction of 0.01, then that would be 1B to 100A, that's 0.01, then the reaction would be driven to the right. So this is why the equilibrium constant is useful in one respect, is it lets you determine which direction a reaction will go if you know the prevailing conditions in a mixture of substrates and reactants. So that is the equilibrium constant. Now you can calculate delta G using the equilibrium constant, and so this is the second really useful thing about the equilibrium constant. So like you remember, delta G, that's a measure, all that is a measure of free energy. So it's free energy change, you know that from chemistry and general biology 1. Is what it really means though, is what it's really useful for, is it tells you how far from KEQ, from the equilibrium constant, a reaction is. And then obviously the further the reaction is from the equilibrium constant in terms of the molar ratio of B over A, the more work that can be done by the reaction, or the more work that's going to be put in to get the reaction to go. So let's kind of look at this equation for a little bit. So to calculate delta G, we've got a number of things going on here. So that's a universal gas constant. So that's 1.987 or something like that. T is the temperature in Kelvin. We'll always use 25 Celsius, so that is 298 Kelvin. Then we've got the natural log of B over A. PR here means the prevailing conditions. So that's B under prevailing conditions, A under prevailing conditions. So that's the product under prevailing conditions over the reactants or substrate under prevailing conditions. Subtracting, again, universal gas constant times temperature, multiplied by the natural log of B at equilibrium over A at equilibrium. And so this value here, B at equilibrium over A at equilibrium, like you just saw, that's the equilibrium constant. So that reaction, or this equation, simplifies to basically the molar ratio of B over A, the natural log of that times this constant here, or the constant R times by the variable T, subtracting RT, natural log of the equilibrium constant. So once you know the equilibrium constant and you know the molar ratio of B over A, you can calculate what delta G is, and then you can rearrange this equation at the bottom if you really want to make it minus RT log equilibrium constant plus RT natural log B under prevailing conditions, A over prevailing conditions, and that gives you the value delta G. So that's how you can calculate delta G, knowing the equilibrium constant and the molar ratio of B to A in a given mixture. Now the thing here is that B and A under prevailing conditions, they have to be stable. So they've got to be, the reactants have got to be supplied to maintain A at the prevailing conditions, and the products B have to be removed by another reaction to maintain B at the prevailing conditions. So there are some things you got to be careful with this stuff, but it's still pretty useful to learn some stuff about the directionality of reactions and delta G. Now, if we look at a little bit more complex situation where we've got A moles of A and B moles of B being converted to C moles of C and D moles of D, that's this kind of standard nomenclature to show this kind of reaction, we can do exactly the same thing. Just because there are more reactants and more products here, we can start to work with the actual concentrations of these things as well. So delta G is now a function of minus universal gas constant times the temperature, natural log of the equilibrium constant. So that's one thing you can calculate out. And then all you have to do is plug in the concentrations of your substrates, your products on the top and your reactants at the bottom under prevailing conditions, and that again will give you delta G. So you can do this when you know the concentrations, the molar concentrations of your substrates and products, and so we end up with this final equation down here once we've got a bit more complicated situation like we have here. Let's look at an actual constant. Let's actually look at an exact example so you can see this being done. Okay, so we want to calculate delta G. Before we get going, the equilibrium constant for this reaction is known to be 0.5. So what that means is that if you've got 1 mole of glucose 6-phosphate, you have 2 moles of fructose 6-phosphate. So that's 1 over 2, that's 1/2. So that's the equilibrium constant for those two. And so this is one of the reactions in glycolysis in the first set of reactions in cellular respiration. So we're looking at the equilibrium constant for this being 0.5, and we want to calculate delta G over here. So what numbers do we have here? minus 1.987 calories per mole Kelvin. That's the universal gas constant. There is our temperature in Kelvin, and there is the natural log of our equilibrium constant determined under standard conditions of 1 molar product and 1 molar substrate. Then we're adding to this value we just calculated, universal gas constant multiplied by the temperature at 25 Celsius, multiplied by the natural log of the prevailing concentration of the product over the prevailing concentration of the substrate. So the prevailing concentration of the product in the cells, usually this is in the red blood cells, is 1 micromolar. Hey buddy. And then the concentration of fructose, the concentration of glucose 6-phosphate is 10 micromolar. So that gives us 10 times 10 to the minus 6 molar. So these are the prevailing concentrations of on top the product and on bottom the reactant. And so when we calculate this all out, we end up with minus 592 calories per mole times by the log of 0.5 plus 592 calories per mole multiplied by the log of 0.1, which is, if you divide this out, you get 0.1. And it all calculates out to negative 954 calories per mole. So what we know now is that this reaction under the prevailing conditions you find in a cell has a delta G of negative 954 calories per mole. All we knew was the equilibrium constant and the prevailing concentrations of the substrate and the product in the cell. And from that, we got delta G. There is a technique called calorimetry, which lets you determine the concentration of products and substrates in cells. We're not going to talk about that technique because we've got too much complicated stuff already in this section. So you can actually do this. It looks like a lot of math and it's complicated, but it's not. A lot of it's just constants. And so once you get used to the constants, this all starts to make a lot more sense. So now the problem here is that a lot of these calculations are done under standard conditions, and delta G will vary under different conditions from standard conditions. So when we're talking about these thermodynamics, we always have to identify the conditions under which the measurements were made. Otherwise, sometimes the equations we use don't apply because the conditions aren't standard conditions. So often we'll hear the conditions being used were standard conditions. So those conditions are 25 degrees Celsius, 298 Kelvin, 1 atmosphere of pressure, and all products and reactants at a concentration of 1 molar. Now, I've already said, well, we've got to consider prevailing conditions, so we already have to take that into account, which is what we just did when we looked at calculating delta G. Now, biochemists, chemists, they do their own thing, that's fine, but biochemists are faced with the reality that cells don't operate under standard conditions. To start with, cells don't work at 25 Celsius, they work at 37 Celsius, in humans anyway. And 1 atmosphere, that's fine, but then we've got things like the concentrations of substrates and products, and then we've got the pH, for example. So when people talk about delta G prime and K prime equilibrium, those are standard conditions, except is what they're looking at are the pH is not 1 molar proton or 1 molar hydroxyl It's 10 to the minus 7 protons, 10 to the minus 7 hydroxyl. That's because the pH is 7. So if you've got a pH of 7, the proton concentration is 10 to the minus 7 molar, and the hydroxyl concentration is 10 to the minus 7 molar also, and they're obviously products to 10 to the minus 14 molar. So when you see delta G prime and K prime equilibrium, we're talking about standard conditions, except the prime is an indication that the pH is at 7 and not at 1 molar protons, for example. And often in reactions, is what we see is water being involved. So water is often a substrate, and water is often a product. Now, water in a dilute aqueous or pure water is 55 molar, 55.6 molar, something like that. So if you have a reaction changing the concentration of water by a micromolar, it makes no difference in the context of 55.6 molar. So biochemists tend to ignore the concentration of water when they're doing these concentrations. So you don't have to worry about water and the concentration of free water in these reactions. So if we then talk about kind of standard conditions, 1 atmosphere, 25 degrees Celsius, 1 molar of each substrate, product, and then pH of 7. We're talking about delta G 0 superscript prime, so delta G 0 prime and K prime equilibrium. So those are under standard conditions. Turns out there is a linear relationship between delta G 0 prime and K prime equilibrium, so the equilibrium constant at pH 7. And that equation is shown here, and it's not too dissimilar to you. Delta G 0 prime is negative universal constant, gas constant times temperature multiplied by the natural log of K prime equilibrium constant. And to that you add the universal gas constant multiplied by the temperature of the log 1, natural log 1. So where does this come from? This tells us that we're dealing with standard conditions, because if we make the substrate concentration 1 molar and the product concentration 1 molar, 1 over 1 is 1. The natural log of 1 here is 0, and so RT times 0 is 0. So this all becomes 0, so plus 0 leaves us just with the negative universal gas constant times temperature, natural log of the K prime equilibrium constant. So that's how you calculate delta G with standard conditions at pH 7. You use this equation here. So what you see from this graph here is that if you have an equilibrium constant of 1, the standard free energy change, delta G 0 prime, is 0 calories per mole of substrates and products. So you can do no work, and no work is required here. Now, if we shift down to an equilibrium constant of 0.1, is what we see then is that standard free energy change is positive, and if we have a value greater than 1, let's say 10, we see that the standard free energy change is less than 0, that is, it's a negative number. And so that is also useful. But you would also learn this just from looking at the equilibrium constant. You could deduce what you see in this graph from the equilibrium constant anyway. So here's our equation from the previous slide. Standard free energy change is equal to the universal gas constant times temperature times the natural log of the equilibrium constant at pH 7. And so if we substitute delta G 0 prime for this value here, now if you remember, this value here was the first variable, the first set of values in calculating delta G prime. Delta G prime is what is biochemically most useful for us. We don't necessarily care about standard conditions. We care about delta G prime. Delta G prime takes into account the prevailing conditions. So these are the concentrations you would find in the cell. Now we've got to take into account the standard conditions, but then we add in this function here, which you've seen before. So delta G 0 prime is this value here, and you saw this equation earlier, and it just substitutes in here. So delta G prime is the standard free energy change plus universal gas constant times temperature times the natural log of the products under prevailing concentrations and the substrates over the substrates under prevailing conditions. And that gives you delta G prime. So you can get all the way here from the equilibrium constant. Okay, so and knowing the prevailing molar ratios of substrates and products in the cell. So where does that take us next? Is what we can then do is we can start to kind of lose this universal gas constant times temperature factor here. So that multiplies out to minus 592. So delta G 0 prime is the same as negative 592 natural log of K of the equilibrium constant at pH 7. So if you start to do all these substitutions, you end up with this equation down here. So delta G under prevailing conditions in the cell is the standard free energy change plus 592 times the natural log of the prevailing concentrations of the products over the prevailing concentrations of the substrates. It looks confusing, but you have to work through it. Your book does a good job of walking through these equations and explaining how you get from the simple equilibrium constant all the way out to being able to calculate delta G prime, and that's what we care about here. So what does this mean? Ultimately, if the K prime equilibrium is greater than 1, then delta G is going to be negative. So standard free energy change here is going to be negative. That means A is going to be driven to B. Okay, that means that spontaneously A will become B. You don't have to do any work because you're going to liberate energy from doing this. So A will be converted to B. Okay, so if the equilibrium constant is down here, so if the equilibrium constant is up here, then we're down here in the negative part of the slope. Okay, so all these values below 0. Now, if the equilibrium constant is less than 1, then the standard free energy change can be positive. We're going to be up here, and the reverse reaction will occur spontaneously. Okay, B will be converted to A. Now, under these conditions here, if you want to convert A to B, you've got to do some work. Okay, so if we flip this arrow around and make A be converted to B, under these conditions, then you've got to do some work. Okay, so there's a lot of math there. You have to work through this slowly. You can do it. There's some simple tricks here. Don't be freaked out by the constants, R and T. Make sure you understand what a natural log is. Make sure you know how to use your calculator. So you can get this done, and I'll have a practice problem we can walk through for this in a moment in the next video. So I'll see you for that soon.